In mathematics, we often solve for x, but what about y? You may have had to memorize the values around a unit circle in class before, and know that the points on the unit circle help us to find the sine and cosine values of different angles. But why does it work like this? The unit circle is simply a circle with a radius of 1, usually centered on the origin. But the special and useful thing about this circle is that if you look at the coordinates along the circumference, the x-coordinates are cosine values of the angle that is created by connecting that point to the center, and the y-coordinates are the sine values. Let me show you an example. The point square root of 3 over 2, 1/2 is a point on the unit circle. Connecting this point to the center creates a 30-degree angle. Or if we use radians instead of degrees, then it's pi over 6. So the cosine of pi over 6 is square root of 3 over 2, and the sine of pi over 6 is 1/2. Is this just some math magic? Let's explore why this is true. Pick a point on the unit circle. I will choose the point AB to represent any point. To plot this point, we would start at the origin and move horizontally by A units, and then from there, move up vertically by B units. Now, if we connect this point back to the origin, you can see that a triangle is formed, specifically a right triangle, since one of the legs is horizontal and the other is vertical. We know the lengths of the legs, but do we know the length of the hypotenuse? Remember that this circle has a radius of 1. Since the hypotenuse is a line segment connecting the center to the circumference, that makes it a radius, which means it has a length of 1. Now, to find the cosine of this angle, which we will label as theta, we take the length of the adjacent side A divided by the length of the hypotenuse 1, which is A, the x-coordinate of our point. To find the sine of this angle, we take the length of the opposite side B divided by the length of the hypotenuse 1, which is B, the y-coordinate. As you can see, the unit circle is an extremely useful tool for remembering and calculating sine and cosine values. Now, this works for all the points on the unit circle, but you'll notice that we usually only label a handful of them. And that's because these are the points associated with some commonly used angles, such as multiples of 30 degrees and multiples of 45 degrees. And that's because they make use of these special right triangles, which have angle measures of 30, 60, and 90 degrees, and 45, 45, 90 degrees. In all of these triangles, the hypotenuse always has a length of 1, since the radius is 1, which makes these values really easy to calculate. And we can utilize these special right triangles to find values around the whole unit circle and just adding negative signs as needed depending on what quadrant we're in. And finally, I want to show you how we can use this unit circle to then graph the sine and cosine waves, and it's almost as if the circle is getting unraveled over time. For example, check out this graph on Desmos, which I'll link in the description. Starting at 0 degrees or 0 radians, the y-coordinate, which represents the sine value of 0, is 0. So we plot the point 0, 0. And moving over through our circle, the sine goes to 1/2, square root of 2 over 2, square root of 3 over 2, and then at 90 degrees, or pi over 2 radians, the y value hits the tallest point at 1. So the sine is 1. Then it continues back down the circle, and then back up until we start all the way back over. This topic leads to many more questions and ideas. For example, why do we even use SOHCAHTOA in the first place to find trig values? And why do we use right triangles, and can we do it using other triangles? But I want this video to be simple and to the point, so perhaps I'll cover those in a future video. But for now, this was What About Why?